The context for problem 2 is a bug. We're given a bug crawling along, presumably in a straight line. Actually, I don't think it matters as long if we just convert this to the distance that it's traveled, or the velocity it's traveled, and we assume our distance is just along its path. So that's all beside the point. The velocity of a bug in meters per hour at t hours is given by this function. V of t is 1 over 1 plus t. I guess as the bug crawls along during this hour, it's getting sleepy and tired and slowing down. We are asked to find the distance the bug crawls in 1 hour. So we are asked to find the integral from 0 to 1 of 1 over 1 plus t dt. This will be the distance in meters that the bug crawls in 1 hour. Oops, the bug crawls in 1 hour. All right. We're told, rather than do a fundamental theorem of calculus, because technically in 5.1 we didn't know it yet, and we're told to use delta t as 0.2 to estimate the distance the bug crawls during this hour. So we're going to set up a table of values with t in hours and v of t in meters per hour every 0.2 seconds. So 0.2 hours, 0.2, 0.4, 0.6, 0.8, and 1. So we have 1, 2, 3, 4, 5, 6. We have 1, 2, 3, 4, 5 intervals. Looks like they want us to use 5 intervals since we're computing its velocity every 1/5 of an hour. So n is equal to 5, and our delta t is equal to 0.2. So let's calculate the velocity of this bug at each of these times. So I just set up my function 1 over 1 plus x. I'm going to be repeatedly plugging things into this function. So I'm just going to set up a table for this value at 0.2, 0.4, 0.6, 0.8, and 1. And here are all my velocities. That's hard to read. But we got 0. It's moving at 1 meter per hour. If it just maintained constant speed, it would go 1 meter in 1 hour, but it's slowing down. So at 0.2, its velocity drops down to 0.83. At 0.4, the velocity is down to 0.71, we'll call it. 0.6 is 0.625, so 0.63. At 0.8 hours, we have 0.56. And at 1 hour, we have 0.5. Yeah, it could be a small bug, and it's not really under any pressure to move quickly. So I guess that's just what's going on here. It's a bug out for a stroll. So remember, we're doing this specifically because we were told to calculate over and under estimates with a delta t of 0.2. If we look at this in a graph, here's what the graph looks like. We can actually calculate the definite integral, because we have advanced math knowledge, from 0 to 1. And we're aiming for a value of 0.693. So we're aiming for a natural log of 2. That's what we're headed for. So let's just keep doing this, though. We're going to do a left 5 approximation. Our delta t is 0.2. And our left endpoints are 1, 0.83, 0.71, 0.63, and the 0.56. So this is a left approximation. Oops. So I have a 0.2 times the 1 plus the 0.83 plus 0.71 plus the 0.63 plus the 0.56 plus the 0.5, 0.846. And this will be the distance traveled in meters. If we do the right approximation, our delta t is 0.2. And we'll just start off with the 0.83, 0.71, 0.63, 0.56, and the 0.5. So really, I'm just going to do the same calculation, and I'm going to change out. Oh, my last one should have been 0.5. I have too many in here. 1, 2, 3, 4, 5. I shouldn't have had the 0.5. So this should be 0.746. So in this one, I want to drop out this 1. I don't want the 1 plus, so I get rid of that. And I want the last one to be at a 0.5. I had too many of them before. So our little bug will crawl somewhere between 0.646 meters and 0.746 meters. So in this case, left is the upper and the right is the lower. We knew that going in because the function is decreasing. If the function is decreasing, then the left will be an overestimate and the right will be an underestimate. The average of these two will be the trapezoidal estimate, and that will be assuming that the function is linear on each subinterval. So it's just a bunch of, instead of a bunch of flat lines, it's a bunch of trapezoids. So the trapezoidal rule, since we have left and right already calculated, I'm just going to find the average of these two. So the reason I'm doing it this way is that I already have these two, so I might as well use them. But we could have calculated this directly by taking the delta t, dividing it by 2 because the average, that's the same 1/2. And what we'll end up with is the one copy of the 1, 2 copies of the 0.83, two copies of the 0.71, plus 2 copies of the 0.63, two copies of the 0.56, and only 1 copy of the 0.5. So remember, if I take the left and right and add them together, I'll have 1 plus 2.83s, 271s, 263s, 256s, and 1.5. And then I average them by dividing by 2. So if I factor out the 0.2, that gets factored out of the sum as well. So if we run this calculation, if I do 0.2 divided by 2 times 1 plus 2 times the 0.83 plus 2 times the 0.71 plus 2 times the 0.63 plus 2 times the 0.56 plus the 0.5 just once, we get the, I didn't put in something right, 283s, 271s, I put 2.63. Two times 0.63, 2 times 0.56, and 0.5. Now we put it in right. Any questions? How's everybody okay? So right now, the difference between left and right is 0.746 minus 0.646. The difference is at a 0.1. So right now we have the distance that the bug traveled within 1/10 of a meter. If we wanted to get that closer, if I took n and went to 10 subintervals and dropped delta t down to 0.1, then the difference between left and right would be within 0.05. So every time I double the number of rectangles, I cut the difference between left and right in half. That's part of what we were talking about last week, where 10 times the amount of work gets you 1 decimal point of accuracy if you're using left and right approximations. Any questions? All right. All right, let's pause the video here and talk about next steps.